So for this section, we are going to look at finding limits algebraically. We've already looked at finding limits with graphs. We've looked at finding limits numerically, looking at tables. We've looked at some properties of limits. So today we're going to start looking at these algebraically, so just from the equations. So our first limit that we have here is the limit of 3x squared minus 4 as x approaches 2. And you guys should be familiar with what this graph looks like more or less. This is a quadratic, except at negative 4. And so we know that a quadratic is continuous everywhere. It doesn't have any holes in the graph. It doesn't have anything that's going to give us a problem. So there should be a limit at every point on that quadratic. So whenever we need to find a limit, the first thing we're always going to do is we're going to plug in the number, because if we can plug a number into the equation and it gives us an answer, then that is the answer. So for example here, I'm just going to plug that 2 right in there for that x. So 3 times 2 squared minus 4. Of course, this is 3 times 4 minus 4. So 12 minus 4 is 8, and 8 will be my answer for this limit. So direct substitution is what we call this. It's as simple as that. You just plug the number in. Number 2 is also just a direct substitution problem. It is very simple, so simple that sometimes it's difficult, because what we're supposed to do here is plug in 0 for our x. However, you do not have an x here, so you don't have anything to plug a 0 in for. So the answer for this is just going to be 5. This is a constant right here, and so you're just looking at a horizontal line if you were looking at the graph, and the y-coordinate of that everywhere is 5. So it doesn't really matter what the limit is approaching. If the limit was approaching 5 or 0 or 1 or negative 1,000, then the limit for this particular equation would always be 5. For our last little example we've got here, we're going to plug in negative 2. So we would have the square root of 6 plus negative 2. Of course, that will be the square root of 4. And so 2 is going to be our answer for that. So direct substitution, very simple. You know, my Math 1 kids don't know about limits, but if I just taught them pretty quick, they could do direct substitution. However, of course, this is not going to stay at a Math 1 level for long, so there are times when direct substitution fails. There are 2 ways that direct substitution can fail. The first is that we have a limit that does not exist, and this is what we're going to see whenever that happens. Here I've got the limit as x approaches 0 of 3 over x. So if I were to plug in 0, I get 3 over 0. Of course, this is undefined. It is not a valid answer. So we would say in this case the limit does not exist. Now when we get a little bit further along, we'll talk about how maybe that limit approaches infinity or negative infinity, but for right now we're just going to say that limit does not exist. The other way that a limit or a direct substitution can fail is you can get what we call the indeterminate form. So I'm going to give you a warning here. I'm getting ready to do something that's technically mathematically incorrect. So I'll show you what it is whenever we get there. I'm going to plug in 5, so I'll get 5 squared. Sorry, I'm having some trouble here. 5 squared minus 4 times 5. Good gracious, this is really driving me crazy. Okay. Times 5 minus 5 over x minus 5. 5 minus 5. And so here we'll get 25 minus 20 minus 5 over 0. And this is going to equal 0 over 0. Now, 0 over 0 is not the same as getting a number divided by 0. A number divided by 0 is undefined, but 0 over 0 is a little bit different. It's what we call the indeterminate form. And 0 divided by 0 is indeterminate because it tells us nothing. There's nothing that you can determine from 0 over 0. Now, I said that I was going to do something that's mathematically incorrect, and I did. I did not make an error with my arithmetic here, but right here is my problem. 0 over 0 is indeterminate, so technically nothing can equal 0 over 0. So writing this way is really not acceptable on the AP exam. However, for right now, I'm going to let you guys do this. For right now, we just need to know that we get 0 over 0, and then the work that the AP exam wants to see is what comes after that. Whenever we get to L'Hopital's rule later, we will have to know about the right way to write that, but we're not going to be doing that right now. So, what do we do if we get the indeterminate form is what we need to know here. So, if you get indeterminate form, you've got to keep going. There's something else you can do if you get indeterminate form. So, I'm going to look at several different strategies that you can use if you get the indeterminate form. And the first one that we're going to look at is factoring and canceling. So, in this case, if I plug in -2 squared minus 3 times -2 minus 10 over -2 plus 2, I'm going to get 4 plus 6 minus 10 over 0, and that's going to give me 0 over 0. Again, it's not quite right to say that equals 0 over 0, but as far as the AP exam is concerned, you can do this part in your head, and you don't have to show that that's the case. What the AP exam wants to see is they want to see this next part. And so what we're going to do is we're going to factor this numerator right here in hopes that something will cancel with the denominator. Now, something very important here that you need to know, whenever we are working with limits, we have to keep our limit notation here until we have plugged in the -2. So at this point, I'm not plugging in the -2. I'm factoring right here. So I have to write this limit notation right out here. Now, it's kind of a pain to write it over and over again, but as far as the AP exam is concerned, you must put that there each time or you can lose some major points. So we've got x squared minus 3x minus 10. That'll factor into x and x. We could do a minus 5 and a plus 2. So the x plus 2's will cancel, and that just leaves us with a limit as x approaches -2 of x minus 5. And now I am going to plug in the -2. So at this point, I don't need that limit notation anymore. I'm going to replace the x with the -2 minus 5. And of course, -2 minus 5 is -7. So that is our answer for this problem. All right. Here's another example that we're going to look at. And this example I used specifically because you may run into something like this on the homework, and I'm not sure if you guys have seen it before. So what we have here is we have x to the third minus 1 over x minus 1. Now you may be tempted to incorrectly cancel these -1s and cancel one of those x's and just have the limit as x approaches 1 of x squared. We cannot do that. That is incorrect because we have these minus signs in between our terms, so we cannot cancel right now. So what we've got to do is we've got to factor this x to the third minus 1. And to factor x to the third minus 1, we have to use the difference of cubes. So we know we have a difference of squares. We also have a difference of cubes. And our difference of cubes tells us if we have a cubed minus b cubed, then that will equal a minus b times a squared plus ab plus b squared. We also could have the same thing with a plus sign in between, and then we would have a plus b here, but we would have a squared minus ab plus b squared. So you can see the difference in the signs there. So in this case, our a, don't forget our limit notation, our a is x and our b is 1. So we would have x minus 1 times x squared plus 1 times x, so just an x there, plus 1 squared, which is just going to be 1. Okay, and then of course this is over x minus 1. So that's a different type of factoring that I am not sure if you guys have seen much before, but it does show up in our homework from our book, I believe. So you may need to look back at this whenever you get to that point. This is called a difference of cubes. And if you're still having trouble with it, you may even want to look up a video on it if you need to. So the x minus 1s, they're going to cancel now. So we're just left with the limit as x approaches 1 of x squared plus x plus 1. And now that something has canceled, that's the cue that we probably want to try direct substitution. So we're going to plug in 1 squared plus 1 plus 1, and we are going to get 3 for our answer here. Before we do our next type of limits, I want us to look at just a review from pre-calculus, and that's rationalization. In pre-calculus, for whatever reason, they have decided that you should always rationalize your answer, meaning that you can't have a square root in the denominator of a fraction. And the good news is in AP Calculus, they do not care if you rationalize your answer. So if you get an answer that's 1 over the square root of 5, then just leave it as 1 over the square root of 5. You do not have to rationalize that answer. However, for the limits that we're going to be looking at, we need to rationalize in order to solve. So I wanted to do these few examples with numbers that you've seen before we try a limit. So if we're just rationalizing something that looks like number 6, we just multiply the top and the bottom of the fraction by the square root of 5. And it's perfectly legal to do that because the square root of 5 divided by square root of 5 is just 1. And if we multiply something by 1, it doesn't change its value. So here we would just get 1 times the square root of 5 in the numerator, so just square root of 5. And then the square root of 5 times the square root of 5 is the square root of 25, which is 5. Or the other way you can think of it is the square root of 5 squared, which is going to give you just 5, because that square root and square are going to cancel out. So that one should be very familiar to you. This next one may be a little bit less familiar because we cannot just multiply both sides by square root of 6 here. In fact, I'm going to do it just to show you why it does not work, because you may not believe me. So here, I'm doing this in red. This is going to be incorrect, so don't do this. You've got 8 times the square root of 6 in the numerator. But right here, you don't just multiply the square root of 6 by this square root of 6. You would have to distribute that square root of 6, which would give you 2 square root of 6 plus 6. And you have not rationalized the denominator here because you still have that square root of 6. So whenever we have a problem like this, 8 over 2 plus the square root of 6, what we have to do is we have to multiply by the conjugate. So the conjugate is going to be the same exact thing here, the 2 and square root of 6, except we're going to have a minus sign in between. And we'll have to multiply by that conjugate in the numerator and denominator. And what we are doing here whenever we multiply by that conjugate is we are creating a difference of squares. So if you remember back to Math 1, you might have x minus 2 times x plus 2. And that's a difference of squares because when you multiply, you get x squared, x squared, and then you'll get a plus 2x and a minus 2x that cancel out, and then you get a minus 4. So the same thing is going to happen down here. So in the numerator, I'm just going to leave that factored. 8 times 2 minus the square root of x, square root of 6. I could distribute that if I want, but I'm not going to. And in the denominator, I would have to FOIL or distribute here, so you get 4, and then you get plus 2 square root of 6, and you get, that one would be minus 2 square root of 6, plus 2 square root of 6, and then minus the square root of 6 times the square root of 6, which is just 6. So whenever you've created that difference of squares, these middle two are always going to cancel out. So what I end up with is 8 times 2 minus the square root of 6 over 4 minus 6. So that is 8 times 2 minus the square root of 6 over negative 2. And then if you want here, even 8 and negative 2 can reduce, so you're going to get negative 4 times 2 minus the square root of 6 here. So that gets rid of the square root in the denominator. It's called multiplying by the conjugate. And it's what we're going to have to do on this next equation here. So I've got the limit as x approaches 0 of the square root of x plus 1 minus 1 all over x. And if I plug in 0 here, I'm not going to write it out, but if I plug in 0, I will get the square root of 1 minus 1, which gives me 0. And in the denominator, of course, I'll get a 0 here when I plug that in. So in order to solve a problem that looks like this, it is often helpful to rationalize either the numerator or denominator. Wherever the square root is at, you want to move it to the other side. So to do that for this problem, we would have to multiply the numerator and denominator by the square root of x plus 1 plus 1. Notice I did not change the sign that's underneath that square root. You leave whatever is under the square root alone, but you change the sign in between your two terms. So whenever I do this, I'm going to have the limit as x approaches 0 of, if I distribute, I've got the square root of x plus 1 times the square root of x plus 1, which is x plus 1. Then I will multiply here, and I'll get plus 1 times the square root of x plus 1. I realize that 1's not necessary. I'm just putting it there in case, so it will help you when you see other numbers there. Minus 1 times the square root of x plus 1. And then negative 1 times positive 1 is going to give you a negative 1. And so what should happen every single time here, if you've chosen the correct conjugate, is these middle two terms are going to cancel out. And so the denominator here, I could distribute, but I want something to cancel later, so I am not going to distribute. It is generally going to be in your best interest to leave the denominator alone whenever you're doing these problems. Now, I've got x plus 1 minus 1 is what I'm left with here. So that positive 1 and the negative 1 are going to cancel each other out as well. So that just leaves me with the limit as x approaches 0 of x over x times the square root of x plus 1 plus 1. And you should see now that these x's will cancel. So now we have the limit as x approaches 0 of, we have to put a 1 up there in the numerator because there's nothing left there, and then square root of x plus 1 plus 1. And so finally we have got something to cancel in top and bottom, and it's probably going to work if we use direct substitution at this point. So if I plug in 0, I've got 1 over the square root of 0 plus 1 plus 1. And so that's going to give me the square root of 1 plus 1, and I'm going to get 1/2 as my answer here. All right, we've got a couple more things that we're going to look at. This next question is a complex fraction, and complex fractions are generally what strikes the fear into math students everywhere. They are an evil concoction of fractions that math teachers have created just to torture you with. So the first step whenever you see a problem like this is to not panic, because they're just fractions and they're not that bad. You can do it. What we need to work with here, we know with fractions that dividing fractions is easy as pie. We flip the second and multiply. Well, that can't really be done whenever you don't have a fraction here. You can do it, but it just makes it a little more difficult. So what I'm going to do is I'm going to get common denominators up here in the numerator. So I have an x plus 2 here and a 2 here. So I'm going to have to multiply this fraction by 2 in the top and bottom. I'm going to have to multiply this second fraction by x plus 2 in the top and the bottom. And so whenever I do that, I've got the limit as x approaches 0 of 2 minus 1 times x plus 2. And since these both now have the same denominator, I can write them all over 2 times x plus 2. I don't have to write those denominators separately. And then this is all over x. Now here I need to distribute that -1. I kept that negative in the parentheses on purpose to make sure that you knew that you needed to distribute, even though they were unnecessary there. So we have the limit as x approaches 0 of 2 minus x minus 2 all over 2x plus 2, and of course all of that there is divided by x. So the positive 2 and the negative 2 are going to cancel each other out here, leaving us with the limit as x approaches 0 of -x over 2 times x plus 2 all over x here. And so we're really close here. We've got this numerator is a single fraction. So at this point, I'm going to tell myself dividing fractions is easy as pie. Flip the second and multiply. So I'm going to end up with the limit as x approaches 0 of -x over 2 times x plus 2 times 1 over x. And whenever I do that, because I've got multiplication here, I can cancel the x in the numerator and denominator. And that leaves me with the limit as x approaches 0 of, make sure you don't lose this negative right here. It's going to be -1 over 2 times x plus 2. And so since we have now canceled something in the numerator and denominator, it is most likely that we should be able to plug in right now. So I'm going to have -1 over 2 times 0 plus 2. And that's -1 over 2 times 2, which is going to be 4. So -1/4 is my answer for this problem. Our last example that we're going to do here is the limit as x approaches the limit as delta x approaches 0 of 2 times x plus delta x squared minus 2x squared all over delta x. And you might be asking yourself, what in the world is that triangle doing in the middle of our problem? You might remember we used that triangle some whenever you were in Math 1. We're doing slope, change in y over change in x. That delta means change in. And this delta x right here, we got to remember that it is a variable. It's like having an h or a c. It is not a triangle times an x. So whenever we do a problem like this, it's almost the opposite of the first problem that we did where we had to simplify, where we factored. For these problems, what we typically want to do is expand. So what we're going to do here is we're going to take that x plus delta x squared and we're going to multiply it out. Now, hopefully, you can do this in your head and square, double square, and say that that's x squared plus 2x delta x plus delta x squared. But if you have forgotten, this is x plus delta x times x plus delta x. And you've got to distribute, so you get x squared times x, plus x plus delta x. Sorry, plus x delta x. And then you'll have another x delta x. And then finally, delta x times delta x is going to be delta x squared. And so that would be x squared plus 2x delta x plus delta x squared. So that's what we're going to do here. And we've got the limit as delta x approaches 0 of 2 times x squared plus 2x delta x plus delta x squared minus 2x squared all over delta x. And we need to distribute our 2 here. So we've got the limit as delta x approaches 0. And that is 2x squared plus 4x delta x plus 2 delta x squared minus 2x squared all over delta x. So you can see here that we've got a positive 2x squared and a negative 2x squared. Those are going to cancel out. And that leaves us with 4x delta x plus 2 delta x squared all over delta x. And in that numerator, we've got a delta x with both of our terms. So what we want to do is we want to do this. We want to do the limit as delta x approaches 0. And then we want to factor out a delta x out of that numerator. So if we pull out a delta x, we'll be left with a 4x here for the first term. And we've got 2 delta x's here where that's squared. So we would be left with just 1 delta x if we pull one of those out. And we still have our delta x in the denominator, which is good because that delta x can cancel with the delta x in the denominator. So this leaves us with the limit as delta x approaches 0 of 4x plus 2 delta x. And this is a little bit strange here because we're only replacing delta x with 0. So when we plug in here, we're going to have 4x plus 2 times 0. We don't need the limit notation anymore because we're plugging the number in. And 2 times 0, of course, is 0. So we get the answer here of 4x. Now, that seems a little bit strange because we're getting an answer that still has a variable in it. There's something very specific that we're going to use this type of limit for in just a few sections later. So you will see these again. But for right now, we're just going to work on using them to simplify. In general, for these problems, your strategy is to expand, and then you'll be left where you have a delta x with everything remaining. You'll factor out that delta x, and it'll cancel with the denominator. So that's generally what you'll do. Your assignment today is going to be on page 84 in your textbook, and you will do number 5 through 17 odd. Those, I'm going to go ahead and tell you ahead of time, are direct substitution. So they should go really fast. Then 51 through 66, you'll have a variety of problems that are similar to what I've done for the examples here. Beware, I believe, if I remember correctly, that there are a few direct substitution problems sprinkled throughout that section as well, and they're typically missed a lot because you're trying to do other things with them. But most of them are ones that you'll have to use the strategies that I've shown in these notes. So when you finish this assignment, take a picture of it and send it to me in my email. Thank you.